Good day, everyone. Welcome to M115 Abstract Algebra. I'm Angel M. Serrano from BSN Math 3A. Today, I'm going to present to you my geometric model, and our main agenda with our presentation is to show that the set of moves in my geometric model forms a group structure. So here's to present to you my geometric model entitled Celangelis-Mandalgebra. So what is Celangelis-Mandalgebra? So let's have a brief description about it. So Celangelis-Mandalgebra is a unique fusion of celestial beauty and mathematical structure. It is built and designed upon an eight-pointed star inspired by mandalas, which are spiritual and geometric representations of the universe. It showcases perfect symmetry with infinite rotational possibilities, embedding algebraic principles through symmetrical transformations like rotations and reflections. At its heart, a glowing A represents my mark and serves as the guiding axis of its symmetries, making it a harmonious blend of celestial beauty and mathematical structure. So in this presentation, I will explain how this model works, starting with its design and structure. Then I will also demonstrate the different moves we can perform in the model, such as rotating and reflecting it. Then I will also show how these moves follow some properties and form what we call a group structure. So let's start our presentation with the design and structure of the model. So the model consists of a front and back side. So as you can see here, the front side is labeled A0 to A7. So we have A0, A1, A2, A3, A4, A5, A6, and A7. While the back part or back side is labeled with letters T, W, I, N, K, L, E, and R. And for a clearer and easier reference, the next slide shows the exact placement of the elements in the front side of the model with their corresponding elements at the back. So as you can see here, the A0 corresponds, or its corresponding elements at the back is T, A1 is R, A2 is E, A3 is L, A4 is K, A5 is N, A6 is I, and lastly A7 is W. Okay, next, let's proceed to the rotational and reflective symmetries in the model. So the model illustrates a total of 16 symmetries, combining both 8 rotational and 8 reflective transformations. So the front part of the model represents the rotational symmetries, while the back part of the model represents the reflective symmetries. So let's begin with with demonstrating all the rotations that we can perform in the model. So in these rotations, we move to counterclockwise direction. So here's the movement of how we rotate, okay, the rotations in our model. So let's begin with A0. So A0 corresponds to do nothing. So which means that we will not move the model. It will just stay in place since we will just do nothing with it. Okay. And this serves as our identity element. Next, we have A1, which corresponds to rotate at 45-degree counterclockwise. So as you can see here, we move our model to 45-degree counterclockwise. Then next we have A2, rotate at 90-degree counterclockwise. A3, rotate at 135-degree counterclockwise. A4, rotate at 180-degree counterclockwise. A5, rotate at 125-degree counterclockwise. Then we have A6, which rotate at 270-degree counterclockwise. Then A7, which rotate at 315-degree counterclockwise. And if we get the full 360-degree rotation of this model, so as you can see here, it will just go back to the original position. So these rotations demonstrate the cyclic nature of transformations, showing that the model returns to its starting position after a full 360 rotation that we have shown here. So as you can see, it will just go back to the original position, or it returns to its starting position, which is the A0. Next, let's proceed to the reflective symmetry. So on the back, we have 8 reflective symmetries labeled T to R, and each represents a specific reflection. So let's first have T. So T corresponds to flipping about vertical axis. So as you can see here, we have the line symmetry, or the vertical line of symmetry. And this line of symmetry, in flipping about the vertical axis, we're going to follow this line. Okay. So next, okay. So let's start by the original position. Okay. So from the original position, by following the vertical line of symmetry, we're going to flip our model from left to right. Okay. So that's how we flipped our model about the vertical axis. Then next, we have W, which corresponds to flipping between left diagonal and vertical axis. So as you can see here, we have the line of symmetry between the left diagonal and vertical axis. And we're going to follow this in flipping our model. Again, starting from the original position, then we're going to flip our model by following the line of symmetry between the left diagonal and the horizontal axis. Okay, so that's how we flip the W. Next, we have I, which corresponds to flip between left diagonal and horizontal axis. And by following this line of symmetry for flipping our I. Okay, starting from the original position again. Then following the line of symmetry, we flip between the left, diagonal, and horizontal axis. Okay, next, have N, which corresponds to flip about the left diagonal. So as you can see here, this is our left diagonal, the line of symmetry for left diagonal. Going to follow this in flipping our model. Again, starting from the original position, then we flip it about the left diagonal. Then next we have K, which corresponds to flip about the horizontal axis. So this is our horizontal axis. Going to follow the line of symmetry and flipping the model. Then starting from the original position, then we flip the model from top to bottom. Okay, next we have L, which corresponds to flip about the right diagonal. So this is the right diagonal, the line of symmetry, and we're going to follow this in flipping our model. Okay, starting from the original position again, then we flip it about the right diagonal. Then next we have E, which corresponds to flip between the right diagonal and horizontal axis. So this is the orange line of symmetry. Okay, as or considered as or E, which flip between the right diagonal and horizontal axis. So next, so again, let's begin with the starting position, original position. Then we flip it between the right diagonal and horizontal axis. Then lastly, we have R, which corresponds to flip between the right diagonal and vertical axis. You will be just following this line of symmetry and flipping the model. And starting from the original position, then we flip it between right diagonal and vertical axis. Okay, so that's how we do the following moves under reflective symmetries. Okay, next. Okay, so we can now define the binary operation star on the set of symmetries. So this operation is defined as the combination of two transformations. Let us begin with A0 star A0. So as I've mentioned a while ago, when we say A0, it corresponds to do nothing. And it also serves as our identity element. So since we operate the combination of two elements, which is to do nothing, the resulting element will just be to do nothing since we do not do any move to either of the two elements. How about when A0 star A1? So since A0 is an identity element, and when we operated any element with an identity element, just in this case A0, the result will just be the element that you operated with it, which is the A1. So since we operated A1 to A0, the resulting element will just be A1. And if we do, okay, the remaining elements, or if we operated the remaining elements to A0, the result will just be this element. So as you can see here, we already plotted with the uh, first results of the row and column. And as you can see, they are similar to the outermost elements of the row by column. Okay, next, what if we have A1 star T? So for our first move, we have A1, which is rotate at 45-degree counterclockwise, followed by the second move, which is T, which is flip about vertical axis. So A1 star T is equal to R. Next, how about W star I? So for our first move, we flip between the left diagonal and vertical axis. Then followed by flip between the left diagonal and horizontal axis. Okay, so W star I is equal to A1. Next, how about A6 star E? So for our first move, A6, we rotate it at 270-degree counterclockwise. Then for our second move, we move it or we flip it between the right diagonal and horizontal axis. So A6 star E is equal to T. Then next, we have K star N. So for our first move K, we flip about the horizontal axis. Then followed by the N, wherein we're going to flip it about the left diagonal. So the result or the result of K star N is equal to A7. And if we operate the remaining two elements, which are the combination of the two movements or of two movements under binary operation star, these are the results. Okay, so this is the table of the summary of the results. Now, let's check if the following movements in the table forms a group structure. And to determine if it forms a group structure, the following conditions must be satisfied. So first, it must be closed, wherein all the resulting elements in the table must be within the set, so nothing shows as outside the set. Then for the second one, it must be associative, and also it has an identity element. And lastly, it has an inverse for all. So let's begin with checking if it is closed. So by observing the results, resulting elements in the table, as you can see, okay, they are found within the set. Okay. So with this we can say that or we can conclude that it is closed. Then next we have or we will check about its associativity. And to check its associativity, okay, first we need to rotate the table to 180 degrees. Okay. Then afterwards, for the step 2, we need to arrange the elements on the rotated version according to the arrangement of the set S. So this is the set S. So as you can see here, or as you observe that the rows in the table are already arranged. Okay, and we will just be interchanging now some columns. So for the first two columns that we're going to interchange is ET. We will and we when we interchange this is the arranged version. And then next, interchanging L and W, the range version, interchanging KI, then interchanging A1 and A7, the next interchanging A6 and A2, and then interchanging A5 and A3. Okay, so now this will be our new table. And for our last step, which is the step 3, we're going to compare the original table to the new table if all the resulting elements are equal to every row and column. Okay, so as you can see here, or as you observe the original and the new table, okay, the resulting elements in both of these tables are the same. So hence, we can conclude that the geometric model or the set of moves in the geometric model is associative. Okay, next we have the identity. So let's check if it is an identity. So since we have already mentioned earlier that A0 is an identity element, so therefore we conclude that identity element exists, which is the A0. Then lastly, how about the inverse? Okay. So with this, we need to show that all the elements of S must have their own inverse element. So for our first step, we need to locate all the identity element, which is A0. So here's all the identity element in each row or column. And then afterwards, we do the process of by row and its corresponding column above will be the inverse of each element. So for A1, A or A0, rather, the inverse element is A0. A1, A7, A, A2, A6, A3, A5, A4, A5, A5, A3, A6, A2, A7, A1. The inverse of T is T. The inverse of W is W. The inverse of I is I. The inverse of N is equal to N. The inverse of K is K. The inverse of L is L. The inverse of E is E. And the inverse of R is R. So as you can see, all of the elements in the set has their own inverse. So we can conclude that all elements in set has their own inverse. Okay, so since we have proven that the conditions that it is closed, it is also associative, has an identity element, and has inverse of for all, therefore we can conclude that the set of moves in our geometric model forms a group structure.